SwayamPrabha. Digital India. Educated India.
Okay, in the last session I introduced this technique called the filtered back projection algorithm, and we went through a sequence of steps that you have to typically follow to implement a very simple version of the filtered back projection algorithm. Now this algorithm itself is fairly old, it has been around for 30-40 years at least, and so there are very sophisticated implementations from a programming point of view. There are parallel implementations, there are filtered back projection schemes with minimal data, with data loss, with limited projections and things like that. We will not have time unfortunately to discuss many of these interesting ideas. Some of them actually constitute areas of research even to this day, because X-ray tomography in general is a very active area of research. Today will be our last session on tomography, and what I will do is I will talk a little bit about more realistic geometries. We spoke about this parallel beam projection, basically assuming all the beams that were coming were parameterized by the same theta and the same, and of course varying t, right, for a given projection, and that is not always the case, right, especially when you go to 3 dimensions. You have a what is called a cone beam. So you have a point source and you have light coming from a point source, X-rays coming from a point source, and so you typically have a cone with its apex at the source and going all the way to the detector, right. Now on the face of it, it looks like a very different proposition, because everything we have done so far has depended on this Fourier slice theorem, and that seems to be the cornerstone for our inversion scheme, and of course the Fourier slice theorem itself was obtained for a parallel beam projection. But it turns out that the corresponding calculations for cone beam, or in 2D what is called a fan beam, are a little bit more algebraically complicated, in the sense that if we go back and look at the geometries for 2D fan beam projections. Now this is a single source, point source, and you have your object like this, and then rays are going out like this. The whole idea behind inverting data that you obtain from this versus data that you obtain from this for the same object, the whole idea is to find a map for rays in the fan beam, find a map to get rays from the fan beam to an equivalent parallel beam, because we know how to reconstruct from a parallel beam. So if you can map somehow the rays from here to this, then we are done, right, rays from here to here. And that really is the crux of the matter, right. The whole algebra, the complication comes up in establishing this map from here to here, right. Now one of the things we want to keep in mind is that if you have a cone beam, now there are 2 different possibilities. If you have a cone beam like this, you can obtain data, let us say this is our source. We will talk about fan beams, right, in 2D, not cone beams are in 3D, we will talk about 2D for now, and then we will come to 3D later. You can obtain data at equal angular intervals, okay, which means your detector is actually a circle, or a part of a circular arc with its origin at the center, at where the source is, okay. So this is arc with center at source. This is the source S. If you do this, then the detectors are spaced, let us say this distance is d, then the detectors are all spaced equidistant but on a curved line, right. This distance is d alpha, this distance is d alpha, and so on. So equispaced but in a line. So this is an equiangular, what is called an equiangular fan beam. Okay. And this will only work when you have a curved detector. So, scheme for mapping this situation to this will be applicable when you have a curve detector. And typically when you go and do a X-ray micro CT, let us say for imaging the brain or somebody's skull or something like that, you will see that they go into this cylindrical structure and the person is placed like this and fed inside, sitting on a bed, and here the detectors are all on a curve. Okay. So, the curved map is a little bit different and you have to take into account the fact that the detector is on a curved line, or in this case a curved surface. The other option is if you have the same object and your source is still the same and you are passing rays again as before, but now your detector is actually a flat panel like this. Typically in your cameras, even your DSLR cameras or phone cameras and so on, your sensor is flat, okay, your sensor panel is flat and the sensors are placed at equal distance, call this delta for example, right. It is an array, it is a 2D array, or in this case it is a 1D array, we are looking at a 2D version, and the 1D array has equal spacing. So, the sensors are all placed in line at equal distance. If you take the corresponding angles, they will be different. Okay, so, they will subtend different angles at the source, but they will have same distances between detectors. So, this is called an equispaced fan beam. Okay, and the map from this to the parallel beam will be a little different from the map from this to the parallel beam. So, you have to worry about which detector geometry you have now, which detector geometry you are dealing with in this case. Okay. Cool. So, how do we do this? Okay, so okay, so I am going to work out some of this geometry very quickly for the equispaced fan beam, not the equiangular case. We will not be able to work through all the details. So, I will give you a reference where you can find much of this information. The book by Kack and Slaney, I might have mentioned it at the beginning, it is called Principles of Computerized Tomographic Imaging. And you will find much of this information in chapter 4 of the book, okay, including for cone beams and so on. For now I will just discuss the equispaced fan beam, so that we are on the same page. The figure that I am going to show you here and the figure on the next slide are both adapted from the same book. Okay. So, I would highly recommend this book because it is a very readable introduction, it is very self contained and it is, in my view, it is a very excellently written book on computer tomographic imaging. It is one of the first books that came out that discussed many of these things in explicit detail, so implementations could be done very easily. So, if you are interested in implementing some of these things, I would highly recommend this book. Okay, so here is a typical equispaced detector. Okay, so our detector is D1, D2, that is right here, and our source is here. Okay, if you take a look at the rays that are emanating, and we are assuming the source is a point source, right. So, the source does not have any dimension, it is a single point, everything is converging to that point, all the rays that are coming here are converging or diverging from the point, whichever way you look at it. Okay, now the book uses the variable s, I will use the variable zeta on the next page because we have used s for the variable along the ray direction. So, just to avoid confusion I am going to use zeta. So, this is let us say zeta equal to 0, this is zeta equal to zeta 1, okay, and this is the intensity that you measure. Now, this is not the same as p theta of t because p theta of t was obtained for a parallel beam, right. This is something else, let us call this r beta of zeta 1 and r beta of zeta in general, okay, zeta being the variable along the detector direction. Now we do not have a single angle in this case, like we had theta in the previous case, we do not have a single angle, because the center line from the source to the center point of the detector, let us say, passes through the origin. So we will make that assumption, the center line passes through the origin, and the angle subtended by the center line is this angle beta. Okay. So that is the only angle we can fix, because if the source and the detector are kept together and either the detector the object is rotated about its axis, or the source and the detector are rotated together about the object's origin as being the center, the only thing that is fixed is this line, right. The other lines are all in relation to this line, but you can get the relative position or relative parameter describing one projection by specifying beta, right. I could as well take some other line here and then say I am going to specify that angle, okay, it is fine, it will just be algebraically more complicated, right. This makes our life easier because it passes through the origin of coordinates. So we will use r beta of zeta, this is analogous to p theta of t, okay. But only remember that beta is only for the center line, not for every single ray. Okay, so here is what we will do. So we will move the detector from where it was. If you go back, the detector was here. So we are going to move the detector to the origin. So we will place it at this d1 prime d2 prime just to make our algebra simpler. So our zeta will not be measured on this distance, but it will actually be measured on the translated detector. Okay. So you have to scale it accordingly, you will have to take this distance and this distance and then use the ratio to scale it, which you can do simple using simple trigonometry. Incidentally, this distance is denoted d. The distance from the source to the detector can be something else, and you have to use that ratio to scale zeta. Okay. So here is our zeta here, and beta is as before. This is the source again, and then these are the beams that are going out. Okay, it is an exaggerated version of the previous schematic. And this is our translated detector. The actual detector was much further down. You go down, and the actual detector was somewhere here, but we have taken it out. Okay. Now, what is our aim now? Our aim is, let us say we have one ray coming like this that has some value of the parameter zeta, okay, we will call this zeta naught, whatever, and its origin from the same source. When the source is inclined at an angle beta to the vertical, the y axis, remember this is the xy axis for the object, this is our line. This line itself is parameterized by two quantities, one of course is zeta and the other is gamma, right. If you change gamma, you will get this line, or you get this line, or you get whatever line, right. So that is determined by gamma, okay, and zeta is the other line as the other variable. Now gamma and zeta of course are not independent, because if you choose some gamma and then you draw a line, it will come and intersect at a corresponding value of zeta, okay. So you can pick either one, either gamma or zeta. In the case of the equiangular distribution, you will use gamma. In the case of the equispaced detectors, you will use zeta, okay, that is the only difference. Okay, now the aim is we take this line, let us take the line SA and we will map it to an equivalent ray in an equivalent p theta of t, okay, that is what we have to do. Once we do that, and if you can do this for all SAs parameterized by beta and zeta, beta being the inclination of the source detector pair and zeta being the intercept, then you have a map from the fan beam to the parallel beam, and if you have a fan beam data, you can generate parallel beam data from that and then do the usual filtered back projection that we already discussed, okay. So that is the logic that we are going to use here. Now how do we do that? The first step is to use some geometry here. So if you look at this dashed line that is here, this line is perpendicular to the line SA, right, this angle is 90 degrees. So if you were to think of this as being some type of parallel projection, this will be the normal, this line will be the normal to that parallel projection. If you remember the parallel projection, this was our object is somewhere here, of course I am not drawing the object because it will interfere with the lines here and make a mess. But if you remember in the parallel beam case, the orientation theta for the parallel beam was given by this angle, right, this angle whatever, correct. This angle was theta, that is exactly the same theta that we have marked here. So, this is a hypothetical theta for an equivalent parallel beam which determines the theta in the p theta. Okay. So, we know theta or we need to know theta, that is what we need to know, right. And how do we get that? Well, if you look at this simple geometry, you know this angle is beta, you know that this S line, the middle line is perpendicular to the detector, right, by definition because the midpoint of the detector. So, this angle is 90 degrees. So, this angle is 90 degrees as a result. So, this angle will be beta, okay, because this angle is also 90 degrees and this angle is also 90 degrees, this will be 90 minus beta, this will be beta. So, the first relation you have is theta is equal to gamma plus beta. Okay. So, you know theta. So, if you are given a particular projection, you know beta, a particular ray in that projection has a particular gamma. So, from that you can get an equivalent theta. So, your first parameter in p theta of t is known. You know which projection in the p theta of t you need to populate with the information coming from this ray, with the r beta of zeta from this ray. But you do not know in what, at what point along the t axis this data has to go, right. So, now we have mapped from gamma beta or a single ray in the r beta of zeta, we have mapped to the theta projection that we need for the parallel beam case, but we do not know what is the t that we need to map to, that single data point that is coming at this detector point A. You can get that by doing somewhat simple trigonometry which is basically looking at this angle. So, this is now t, right, because this is your hypothetical p theta of t plane, the line whatever. So, this is t from the origin till the point at which it intersects the plane, just like we had here, right, this was t, for this ray this was t, right. So, now this for this ray S A, this is t. So, you need to know what t is, and how do you do that? You write t by zeta, t by zeta is cos of gamma in this triangle, right. You have t, you have zeta, t by zeta is cos gamma. So, now you know which t to map to, right. How do you get gamma now? Gamma is okay, gamma, if you knew equiangular you knew what gamma was, but now if you have an equispaced detector you can get gamma simply by writing tan gamma is zeta by d. Tan gamma in this triangle is zeta here divided by d, distance of source to detector. So, if you know r beta of zeta, then you can first get gamma of course using zeta by d. D is a fixed value because it depends only on the distance between the source and the detector. So, you can now calculate gamma. Once you know gamma, you add gamma and beta, you will get theta. Okay. For a given zeta value, you do t by zeta is equal to cos gamma, you get gamma, you add it to it, you get theta. So, you know in what, if you remember our discussion, the sinogram business, right, you had t going like this and you have theta going like this. Remember, and you had this thing that looked like this, I showed you an example in the last session, maybe a couple of sessions ago. You know the theta coordinate from this equation, from 1 you know the theta coordinate. So, you know where on which slice to update. Okay. From 2 you know the t coordinate. So, you know where to come over here, at what point to update, right. So, this value will be equated to this value in the fan beam projection. So, now you run through the entire fan beam projection, calculate t, calculate theta, and then you start updating all the points with the data from the fan beam projection, you will get an equivalent parallel beam projection, and now from here you do the filtered back projection and you will get the final reconstruction. Okay, that is the simplest, most conceptually clean way of doing this. Okay. Now, there is a slightly more sophisticated way of doing this using the impulse response function. I will not discuss that here for want of time, but if you go back and look at the reference I provided on the previous slide, you will find details on how this implementation is done. Okay. Okay, so that was about the fan beam. So, this is how you would do a reconstruction for the fan beam, for the equispaced fan beam. Now, I will just talk, just for completion's sake, I will talk about the 3D cone beam case. The geometry is the approach is very similar. You have to just do the following. So, let us say I have a 2D equispaced 2D detector. So, each point here is 1 pixel, let us say whatever equivalent of the CCD in your DSLR. It is an X-ray detector, it is just 1 pixel, and you have a source that looks like this, and then you have a beam that is going out like this, and it is going to generate data on a certain set of pixels. The idea here is exactly the same as the idea that we used for the fan beam case. Okay. So, you take each cross section, in each cross section you will have a fan beam going like this in each cross section. So, this is a cross section, you will have this will be a fan beam. So, once you have the fan beam, you map to a parallel beam, and from there you do the filtered back projection to get the data in this particular cross section. Okay. And then you go back to the next section, you have an equivalent fan beam, but now if you look at this fan beam, I have drawn it exactly in the same plane containing the detector and the source point. But if you go a little up, then your fan beam is basically tilted, right. So, now you will have some additional geometric relations to basically project this back down to this parallel plane, and then use this to map out an equivalent location for an equivalent parallel beam, and then do filtered back projection for that, right. So, there will be some correction depending on this inclination angle, which we will call delta maybe. Okay, so, if you look at the side view, this is a source, this is a detector, this cross section is easy, it is just straightforward, it will be a fan beam in this plane. But if you look at this cross section at an angle delta, this cross section, now you will get information on an angled plane. So, you have to be careful in how you interpret it, right. And the reason you have to be careful is that the detector now the distance will change. So, you have to do something equivalent for a point here, for a point here. So, you get cross sections like this. Okay, if you do the same slice by slice fan beam business that we discussed. There is a slightly more geometrically cleverer way of doing this, which is basically to take each of these in a cone beam and map it back to parallel sections like you did for the 2D case, but now for the 3D case. Okay. And this method is called the Feldkamp reconstruction method. It is analogous to what we have discussed so far of back mapping using simple trigonometry, and you will find details of this in the book that I have discussed. Okay. It is slightly more tricky to implement, but it is based on essentially the same ideas that we have discussed so far. Okay, and this is how typically cone beam reconstructions are done, right. Again, it is just a map, slightly more sophisticated map, but it is a map to come back to a parallel beam type case and then use this Fourier slice in the form of a Fourier in the form of the filtered back projection scheme. Okay. So, with that I will just wrap up our discussion about tomography. So, the basic idea is you have first of course transmitted light, and you are looking at basically absorption measurements. Okay, unlike the other cases where you are looking at changes in polarization or changes in refractive index, changes in speed. Now, you are looking at absorption. We set up this using this Beer-Lambert law. Right. and then we said that you have to find f of x y from a series of projections which we call p theta of t for various values of theta. These were all parallel projections. And then we derived this Fourier slice theorem to relate Fourier transforms of p theta of t, which we called s theta of w, to the 2D Fourier transform f of u v along a radial line. And then we reinterpreted this Fourier slice theorem to come up with a filtered back projection. Algorithm, which is a very clever and efficient way of implementing this inversion scheme based on the Fourier slice theorem. And then we saw how to map various geometries, various source detector geometries. Okay, so if you have a fan beam, as you have a cone beam, equispaced, equiangular and so on, right. And this only used simple trigonometry, and then it basically fed back into this, and then from there you could again go through the same sequence of steps. Okay. Now the whole idea of X-ray tomography is an area of active interest. There is a lot of research that is still being done in this particular domain. What we have done is barely scratch the surface. There are lots of interesting topics that you could pursue from here. I hope this will give you a background for getting started. For instance, this idea of using multi-energy X-rays to get spectral information is something that is very actively used both in defense applications, airport security. We mentioned some of that at the start. There is also inversion with limited data. So, for example, if you are trying to reconstruct the internals of a pipe where you do not have access to the entire 3-dimensional pi degrees of rotation, you only have data that you have taken from a few angles. Let us say a pipe is like this and you have only taken a few angles on the top. How do you reconstruct from data that is restricted to a certain domain in the theta plane? That is another area that is of active interest. And there are also more sophisticated techniques. So, for example, if your material is not just absorbing but also diffracts, right. If you have a crystalline sample and you have a very high fidelity X-ray detector and you have diffraction effects, how do you account for that? How do you use that to interpret something about the system while also interpreting this f of xy type of function? So, there are lots of possibilities and lots of possible directions to take this work in. The book that I had mentioned is a good starting point, although now it is a little bit dated. It is about 3-4 decades old. There are more recent monographs that you can get started on, but hopefully this will give you some background on which you can build your future investigations in this particular area. So, with that we come to the end of this entire module on optical methods for solids. As you can see, the area is quite rich. There are quite a few techniques. Some of them are new and they are being readapted to more contemporary applications in solid mechanics. Some are old and they are still being used and they are very profitable, like X-ray tomography for instance. And so it is an area that is very fundamental to our understanding of mechanics, of deformation, of internal structures and things like that. There is increased emphasis on some of these ideas more recently with advances in manufacturing technologies, in production, inspection, quality control, things like that. And so I hope that this entire set of a dozen or so, 3 dozen modules has given you some idea of how to get started, what some of the basic techniques are and how you can implement them in your own setting for your own application, and hopefully it will spur you to investigate some of these techniques in a little bit more detail and try and understand them at a slightly more deeper level than we could cover here. So, with that we will sign off in this course on optical methods in solids and fluids, and I hope you have learnt significantly new information over the last 20 hours.